Bismillah ar-Rahman ar-Rahim. So today we will discuss lecture 2 of chapter 22, Gauss's law, and we will talk about the application of Gauss's law to determine the electric field produced by a point charge. Secondly, the electric field due to the spherical symmetric charge distribution. Of course, we will discuss inside the field and outside the field. Then we will discuss the electric field due to a thin spherical shell. Inside the spherical shell, what is the electric field? And outside the spherical shell, what will be the electric field? Then we will discuss the electric field due to the cylindrical symmetric charge distribution. And here we will talk about a very long charged wire, and then we will talk about infinitely long charged cylinder in the volume. The last example that we will discuss is the electric field due to non-conducting infinite current. Okay, so let's make a short review as usual. So as you know, Gauss's law is the following. The electric flux is equal to the EDA through closed surface, which is equal Q, the charge inside the closed surface, that means Gaussian surface, divided by epsilon naught. And here we will denote this term by left-hand side and this term by right-hand side. And each term is equal to the electric flux. Okay? So to apply Gauss's law, what we must follow, we must at first define the Gaussian surface. Gaussian surface. If we are talking about a point charge is considered as a sphere, so we will take Gaussian surface as a spherical surface with a radius r. Then, if we are talking about the sphere, of course, Gaussian surface will be sphere. If we are talking about an infinitely long wire, that means Gaussian surface will be a cylinder with radius r and the length l. The same case for infinitely long charged cylinder. And then, if we are talking about charged surface, that means infinite surface, infinite sheet. In this case, the Gaussian surface will be a cylinder with a surface area A. So this is the definition of the Gaussian surface. Then we will define the left-hand side. Determine left-hand side. EDA, which is equal, it's dot product between the electric field and the vector, the infinitesimal vector area A. So we will denote it as the magnitude of E multiplied by magnitude of A multiplied by cosine of theta between the vector A and the vector area dA, the vector E and the vector area dA. So here we will talk about two configurations. If we are talking about a charged cylinder, for a charged sphere, if we are talking about sphere, Gaussian surface is a sphere. In this case, the surface area of the sphere is 4 pi r squared. But if we are talking about a cylinder, the surface area of the cylinder is 2 pi r multiplied by the length of the cylinder. So at first, you must memorize these two equations. The surface area of the sphere is 4 pi r squared, and the surface area of the cylinder 2 pi r L. So this is the first term. The second term is Q inside the Gaussian surface divided by epsilon naught. Okay, that means we have to determine the electric field. Fourth step is left-hand side equal right-hand side. And like that, we can conclude the electric field, whatever it's outside or inside. Okay? So we will try to follow these 4 steps to determine the electric field due to point charge. Starting with Gauss's law, calculate the electric field due to an isolated point charge and show that Coulomb's law follow that this results. At first, this question is composed of 2 questions. The first question is the determination of the electric field produced by a point of charge using Gauss's law. The second question is the demonstration of Coulomb's law from Gauss's law. Okay, as usual, you know that we want to demonstrate the results step by step. Let's take a positive charge Q and a point P. The positive charge produces an electric field outward because it's positive. Okay, Gauss's law said the electric flux equal EDA, which is equal Q inside divided by epsilon naught. Step number one, what is Gaussian surface? Gaussian surface in this case is a spherical surface. Why? Because we consider a point of a charge, as a sphere. Okay, so let's say Gaussian surface is a Gaussian surface is spherical surface with radius r. But there is a small condition about the spherical surface. This spherical surface should be concentric spherical surface. What means concentric spherical surface? The word concentric means that the center of the charged point of the point charge is the same center of the spherical surface of Gaussian surface. Okay, so we will try to draw this Gaussian surface. So let's assume that the point P belongs to the Gaussian surface. Okay, now what we must draw? We must draw the vector dA, the vector dA, vector area. Okay, the vector area dA is perpendicular to the Gaussian surface. Okay, so it will be perpendicular to the Gaussian surface like that, dA. Now, what is the angle between dA and the vector E? Theta is 0. Very good. So the second step, left-hand side. Alas, we are done with the first step. The integration of EDA, which is equal, we have here dot product, so it will be the integration of E multiplied by the vector area A, dA multiplied by cosine theta. What do we said about theta? Theta is 0, so that means cosine theta equal 1. Okay? Cosine theta equal 1. So what we're going to write? We will write the following. So the left-hand side, it will be E. E is uniform, so we can write E out of the integration of dA multiplied by 1, so that means cosine 0. So what do we said in the first slide about the integration of dA? So it's only EA. And A for the sphere, the surface area of the sphere, we said it's E 4 pi r squared. So this is the left-hand side. Now let's move to the right-hand side. For the right-hand side, what do we have? Right-hand side, Q inside divided by epsilon naught. This is the Gaussian surface in blue. What is inside the Gaussian surface? We have the charge Q. So let's write Q divided by epsilon. This is the second term, the right-hand side. From the left-hand side and the right-hand side, we can conclude that E 4 pi r squared equal Q divided by epsilon naught. So we can write E equal Q over 4 pi epsilon naught r squared. And this is the electric field produced by point of charge using Gauss's law. It's okay. So what do you know about K? K, the Coulomb's constant, is 1 over 4 pi epsilon naught. So we can write so that the electric field E is KQ over r squared. And this is our electric field produced by point of charge. The second question, imagine that if we place a pointed charge, at this position, at this location, at the point P, we will place a point charge. Let's put here positive point charge Q naught, which is a tester charge. Okay, what will be the electric force in this case? The electric force, as you know, is Q naught multiplied by the electric field at that point. Okay, the test charge Q naught multiplied by the electric field at the location of Q naught. So it will be Q naught multiplied by the electric field using Gauss's law. It's KQ, it's KQ over R squared. Okay, so if we take it as a function of a vectorial relationship, so we can write here a unit vector R. Okay, so what will be F equal K Q Q naught divided by the distance between them squared multiplied by the unit vector R. What is this? This is Coulomb's law. Okay, this is Coulomb's law. So starting from Gauss's law, we can demonstrate Coulomb's law. Okay, and we are done. So we can say, let's place a second point of charge Q naught at the point where the electric field is E. The electric force on the test charge is Q naught multiplied by the vector electric field E. So in this case, we will demonstrate that the electric force is KQ1, Q2 divided by R squared, which is Coulomb's law, as we said. Okay, first we are done with the first example, point of charge. Now we will discuss the example of an insulating sphere of radius A, and a uniform charge Q. This Q is distributed over the volume of the sphere. Okay, so it's a volume distribution. Volume distribution. Okay, good. Question number 1A, calculate the magnitude of the electric field at a point outside the sphere. Outside the sphere. Let's try to do the example step by step. Okay. Good. Okay, so what do we have? We have a charged sphere. This is the center. This is our sphere. Good. With a radius. With a radius what? With a radius A. And he's asking to calculate the electric field outside the charged sphere. Okay, so step number 1, define the Gaussian surface. Gaussian surface, let's write here outside. Question A, outside. Gaussian surface, we are talking about a charged sphere, so Gaussian surface will be a Gaussian sphere. Gaussian surface is a spherical surface, is concentric. Spherical surface. Concentric spherical surface. Okay, with a radius R. And this R is greater than the radius of the charged sphere A, because we are talking about outside. Okay, so then the left-hand side, we said the left-hand side is the integration of the dot product between the vector electric field and the vector area A. Okay, so what will be? It will be the integration of E dA cosine theta. If we take, for example, a point P on the Gaussian surface, so the electric field at this point is outward because we are talking about positively charged sphere. So this is the electric field. What about the vector area? It's perpendicular to the surface, so it will be also in this direction. What is the angle between them? Theta equals 0. That means cosine theta equal 1. So this cosine equal 1. So we get the left-hand side, it will be equal E multiplied by A of what? Of a sphere. So in this case, as we said in the previous example, the left-hand side gives E for pi R squared. And this is what we call the surface area of the sphere. This is the first term. Let's move to the second term, to the third term, sorry. The third term, we want to calculate the Q inside divided by epsilon naught. What is inside the Gaussian surface, the surface on blue? It's the total charge Q, because we said in the question, with has a uniform charge Q distributed over its volume. So let's write U divided by epsilon naught. And this is our second term. First term plus equal to the second term gives what? Gives E 4 pi r squared equal Q divided by epsilon naught. That means our electric field E equal Q divided by 4 pi epsilon naught r squared, which is equal Ku over r squared. This is the electric field outside the charged, the charged sphere. And we are done with the first question. Now on the second question, he said, what will be the electric field inside, B, inside. For inside the Gaussian surface, in this case, it will be inside the charged sphere. As usual, Gaussian surface is what? Is a spherical surface because we are still in the charged sphere. Is a spherical surface. As usual with radius. The radius r. And as I told you, this r is smaller than the radius of the charged sphere. Why? Because we are talking about inside the sphere, and this spherical surface should be also concentric. That means the charged sphere and the Gaussian sphere should have the same center. So خلاص, we are done with the first step. Let's move to the second step. Left hand side, as usual, the left hand side for the case of a spherical surface, it will be spherical Gaussian surface. It will be the integration of EdA, which is equal directly. خلاص, now we know how to get the result. E 4 pi r power 2. Okay, let's move to the left hand side, right hand side. For the right hand side, what do we have? Q inside divided by epsilon naught. But we have to be very careful now. Now we are inside, not outside. If we are outside, we will take the total charge. But if we are inside, we will take an amount of charge, not the total charge, a portion of charge. Okay? So how to calculate this portion of charge? What I said here in the question. In the question, I said it's volume distribution. When we are talking about volume distribution, the total charge equal what? Equal rho multiplied by V. Okay? V of what? V of the charged sphere. But now we will not take the total charge. No, we will take a portion of charge, Q inside. Q inside, it will be equal rho multiplied by the volume of the Gaussian surface, of the Gaussian sphere. Gaussian sphere. And to calculate the right-hand side, we have to divide by epsilon naught. What is rho? Rho is called the volume charge distribution. Volume charge density. Charge density. Okay. The volume charge density. خلاص, we are done. What is the volume of the sphere? So Q inside divided by epsilon naught, it will be rho multiplied by the volume of the sphere. What is the volume of the sphere? It's 4 over 3 pi r cubed. But don't forget, we have to divide by epsilon naught. So 3 epsilon naught. Okay. So this is our second term. This is our first term. First term equal to the second term gives what? E equal, let's write E 4 pi 4 pi r squared equal rho 4 pi r cubed divided by 3 epsilon naught. So you see here that we have 4 pi and 4 pi, they will cancel each other. We have power 3 and r power 2. So that means our electric field is equal rho multiplied by r divided by 3 epsilon naught. This is our electric field inside the charged sphere. So we are talking about the radius of the Gaussian surface smaller than the radius of the charged surface. Okay, so let's summarize. If we want to summarize, E outside, we said it's KQ divided by R power 2. E inside, we said it's rho R divided by 3 epsilon naught. If we want to write this equation, the second equation, the electric field inside, as a function of the total charge Q, what we're gonna write? Don't forget that we said here, the total charge is rho multiplied by the volume of the charged sphere. We have, okay, so let's write a question. Write E inside as a function of what? Of the total charge Q. We know that Q equal rho multiplied by the volume of the charged sphere. So it will be equal rho multiplied by 4 over 3 pi a power 3, a cube, not r cube. We are talking about the charged sphere, the volume of the charged sphere. So that means our charge density rho equal Q multiplied by 3 divided by 4 pi a power 3. We will take this charge density rho and we will substitute the expression by the expression in the inside the electric field inside the charged sphere. So that means our electric field inside will be equal rho. How much is rho? Rho is 3q divided by 4 pi a cube multiplied by r divided by 3 epsilon naught. Don't forget that this term is the charge density rho. So what we have here to cancel. So we have 3 and 3. So the electric field inside it will be QR divided by 4 pi epsilon naught. 4 pi epsilon naught. A power 3 a cube. So this is E inside. We substitute 1 over 4 pi epsilon naught by K. So we got K Q R over A power 3. And this is our electric field inside the charged sphere as a function of the total charge Q. Okay, so we are done. Just I want just to draw the functions. So we have E outside is KQ over R squared. E inside it's KQR over A power 3. Okay, so now we want to draw these two expressions, these two electric fields. We have the electric field as a function of the distance r. We have a specific point when r equal the radius of the charged sphere. For outside, for the electric field outside, if r is infinity, what happened to the electric field? It's varying as a function of 1 over r squared. That means the electric field is 0. Okay? Now, if r is 0, we are inside. In this case, the electric field varies as a function of r, so it would be 0. Okay? Now we have a specific point. If r equal a, r equal a, from the first equation, what would be? For r equal a, the first equation gives kq over a power 2. Okay. For the second, KQA over A power 3. So that means it will be also A power 2. So we have the same expression. And we call this electric field E max. What is the maximum electric field? The maximum electric field is when R equal A, and it's equal KQ over A squared. This electric field is KQ over A squared, and it's called E max, the maximum electric field. When we are inside, the electric field is varying as a function of R, so it's linear function, increasing proportional to R. When we are outside, the electric field varies as a function of 1 over R power 2. So it would be like that. So it's proportional to 1 over R squared. Okay? So this is the variation of the electric field as a function of the distance R. So what we can say here, the E outside when R equal A equal E inside when R equal A. So what we conclude? We can conclude that the electric field produced by the charged sphere is a continuous distribution, a continuous field of the surface. Okay, fellas, we are done with this example. Now we will take another example. The second example said, okay, we are done. Okay, so we will take another example. Okay, so this example. He's asking here, a thin spherical shell with inner and outer radii are almost equal, of radius r, and has a total charge q distributed uniformly over its surface. So we have a spherical charge distribution. The question, calculate the electric field outside and inside the spherical shell. So what we're going to do, it's very easy. Using Gauss's law, it's very easy. When we are outside, inside, we will repeat the same steps. Inside, that means Gaussian surface radius is smaller than the radius of the charged spherical surface. Okay, so the first step, define Gaussian surface. Gaussian surface is what? Is a concentric spherical surface with radius r. Second step, left-hand side, which is equal the integration of EDA cosine theta. If we take, for example, so we have the same thing, so we will write E for pi r power 2. Okay, third step, right-hand side. What will be the right-hand side? The right-hand side gives Q inside divided by epsilon naught. But we are inside the charged sphere, and this sphere is charged on the surface. That means no charge inside the spherical, the surface charged sphere. Surface charged sphere. Why? Because it's charged on the surface. Okay, so Q inside it will be what? Q inside it will be equal to the 0. So this is our first term. This is our second term. First term equals second term, so we can get E for pi r power 2 equals 0. R is different to the 0. 4 pi is different to the 0. That means our electric field inside the spherical shell is 0. It's okay. Why? Because we don't have any charge inside this spherical surface. We have a sphere charged on the surface only. Okay. Now we can move to the second step. For the second step, what we're going to do? And the second step, we will try to calculate the electric field outside the charged surface. Outside. Okay. What is the figure of outside? Yeah. We will do the same steps. Gaussian surface is the same. When outside, that means the radius of the Gaussian surface is larger than the radius of the charged sphere. Gaussian surface is a concentric. Spherical surface with radius r, but r in this case is larger than the radius of the charged sphere, charged shell. Second step, left-hand side, integration of ETA, which is equal to integration of ETA cosine theta. As usual, we said cosine theta is 1, so we will write this term equal E 4 pi r squared. And this term is what? Is the integration of dA for spherical surface. Okay, so this is our first term. This is the fourth time that we are repeating these steps. The second step is the right-hand side. And we are outside. That means R larger than A. So Q inside divided by epsilon naught gives what? If we are outside, what do we have inside the Gaussian surface? We have the total charge Q. Okay, we have the total charge Q. So Q divided by epsilon naught. And this is our second term. First term and second term gives E equal Q divided by 4 pi epsilon naught r squared, which is equal KQ over r squared. And we are done. This is the electric field outside the Gaussian, outside the spherical shell. Okay, so this is, we are done. If we want to draw the electric field, what do we have? We have E inside, E outside equal KQ divided by r squared. E inside is 0. Okay, so this is the electric field as a function of the distance r. We have a specific point when r equal the radius is of the charged shell. Inside, it's always 0 because the charge only on the sphere, only on the surface of the sphere. Outside, it's varying as a function of 1 over r squared. Varying as a function 1 over r squared. Okay, and this is E equal 0. As you see here, we have E outside when r equal A is different to E inside when r equal A. In this case, we cannot say that the electric field is continuous, but it's discontinuous when at the surface of the shell. And we are done. Okay, you see it's very, 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 very easy. Now we will discuss another example. This example says, find the electric field of a radius r from uniform positive line charges of infinite length whose charge per unit of length is lambda, and lambda in this case is constant. Now we are talking about the linear charge distribution. Okay, the linear charge distribution. Let's take our figures. What do we have in these figures? Actually, we will demonstrate the same equation given in chapter 21, lecture 3. In chapter 21, lecture 3, we said if we are talking about infinitely long charged wire, in this case, the electric field at a distance x, it will be 2k lambda over x, and x is the distance between the charged wire or the charged rod and the point P. Okay, but in this case, we demonstrated in the lecture 3, we demonstrated the electric field to be K, the integration of TQ over R power 2. Okay, using this equation. But now we will use Gauss's law. Gauss's law said, first step, Gaussian surface is what? We are talking about a charged wire. A charged wire, it's infinite cylinder, infinitely long cylinder with the radius very small. So Gaussian surface will be what? Gaussian surface is a a concentric cylindrical surface with radius R and length L. Okay, this is the first step. The second step, left-hand side. On the left-hand side, we want to demonstrate, to calculate EDA. We said its dA is the dot product between the electric field and the vector area dA, sine theta. So we will introduce cosine theta. You see here that the electric field is radially outward because it's charged positively. And of course, the vector area dA is perpendicular to the Gaussian surface. So the angle between them is 0. That means cosine theta is 1. Okay, the electric field is uniform, so it will be only the integration EdA for cylindrical surface. Cylindrical surface. In the first slide, we said that dA, the integration of dA for cylindrical surface, it will be left-hand side E multiplied 2 pi R multiplied by L, the length of the rod, the length of the Gaussian surface. And this is our first term, left-hand side. Now let's move to the second term, right-hand side. We are outside because we are taking the wire with very small radius. Okay, so right-hand side, Q inside divided by epsilon naught. Q is what? Is lambda dL. Okay, Q is what? Is lambda L. Lambda, not lambda. dQ is lambda dL. Lambda multiplied by the length of the wire divided by epsilon naught. This is our second term. You see, in 2 steps, we can get the electric field to be lambda L divided 2 pi RL. 2 pi RL multiplied by epsilon naught. So you see here that we have L and L, so we cancel it out. So the electric field, it will be lambda divided by 2 pi epsilon naught R. If we want to write the equation as a function of K, so what we're going to do, we will multiply here by 2 and here by 2. Why? Because 1 over 4 pi epsilon naught, it will be K. So let's write 2K lambda divided by R. And this is the electric field produced by infinitely long wire. Okay? So, خلاص, we are done with this example. Let's move to another example. Now we will talk about cylindrical symmetric charge distribution. In this example, he said, find the electric field a distance r from uniform charged cylinder of infinite length whose charge per unit of volume is rho, and this charge density is constant. What we're going to do in this case? Of course, we will try to calculate the electric field inside and outside the volume charged cylinder. Let's start by inside. Where is it? The figure. Okay. Let's start by inside. Okay. Inside. Gaussian surface, Gauss's law said what? At first, we have to demonstrate, to define Gaussian surface. Gaussian surface is, is what? Is a concentric, cylindrical surface with radius r and length L. Very good. This is the first step. The second step, the left hand side. The left hand side said what? EDA. But here we have to be very careful because we have different cases. The first one, we have the sides, the electric field produced by the side. It's radial. Okay. The electric field produced by the ends. Okay, good. But here we said infinitely longer, infinitely longer. So we don't have this one, don't have this one because it's infinitely long. So what we're gonna write? This expression, the integration of EDA, it will be EDA of the ends plus EDA for the sides. For the ends, it will be 0, okay? Infinitely long. So it will be only for the sides. For the sides, it will be E, the integration of the A. Let's go step by step. So we will write EDA cosine theta. The vector dA, the vector area dA is what? What is it? It's radial. Okay, it's perpendicular to the Gaussian surface. Whatever it's inside or outside, in the same cases, the vector dA is perpendicular to the Gaussian surface. So it's also radial. So that means theta equal 0. That means cosine theta equal 1. So this cosine theta equal 1. The electric field is uniform. That means the left-hand side will be only E, the integration of the A. The integration of the A is what? For the spherical surface, cylindrical surface, sorry. Cylindrical surface. In this case, it will be E 2 pi R multiplied by the length of the cylinder, Gaussian cylinder. Okay, so this is our first term. Let's move to the second term. For the second term, right-hand side, Q inside divided by epsilon naught. We said that we are inside the charged cylinder. Inside, that means R smaller than A, okay? So what we're gonna do in this case, Q inside, it will be, we will take a portion of charge, not the total charge. But we know that Q is rho, the volume density, the volume charge density, multiplied by V of Gaussian surface, Gaussian cylinder. Okay, what is the volume of the cylinder? By R squared multiplied by the length. This is the second term when we are inside. Okay, if we are outside, we will take the volume of the charged cylinder, not the Gaussian cylinder. Okay, so equation 1 equal to equation 2 gives E 2 pi R L equal, we forget that divided by epsilon naught, divided by epsilon naught, equal rho by r squared L divided by epsilon naught. So what we're going to simplify here, we will simplify L and L, R squared and R. So we get the electric field inside the charged cylinder equal rho R divided by epsilon naught. Okay, for outside now, for outside, the first term is the same. The first step for Gauss's law is the same. Gaussian surface is the same. For the second term, left-hand side, it will be the same. Outside, that means R larger than A. Left-hand side, it's the same, E 2 pi RL. Right-hand side, in this case, it will be Q inside divided by epsilon. And in this case, Q inside, it's the total charge, Q. And Q is what? Is rho multiplied by V. Which V? V of the charged cylinder divided by epsilon naught. Okay, it will be rho multiplied by pi A squared multiplied by L divided by epsilon naught. This is the second term, this is the first term, and like that we can get our result. Oh, sorry. Term 1 equal term 2 gives E 2 pi R L equal rho multiplied by pi R squared L divided by epsilon naught. Okay? Sorry, A squared, not R squared, A squared. So what we will simplify? We will simplify this and this. I think that we made a mistake here. What we simplified, we forget these two. Yeah, we forget these two. We did not simplify the two. Okay, so we will simplify L and L. In this case, E outside, it will be rho multiplied by A squared divided by 2 epsilon naught. And this is the electric field outside. Okay, let me check the results. Yeah, 2 epsilon naught R. That is the R, I think. Yeah. Forget this R also. Okay, خلاص. It's varying as a function of 1 over R. So as a summary, E inside equal E inside rho R over 2 epsilon naught. E outside rho A squared over 2 epsilon naught R. Okay, but you must know how to convert this rho as a function, how to convert the electric field, how to write the electric field as a function of the total charge Q. Okay, to do that, we know that Q, the total charge, is rho multiplied by V of what? Of the charged cylinder. Okay, whatever. Let's come back. So if we want to draw these two cases, these two electric fields, inside and outside, we have the electric field as a function of the distance r, and we have a specific point when the distance r is equal to the radius of the charged cylinder. In this case, if we are inside, that means r smaller than a. In this case, it's varying as a function of r, so it's linear function. Varying proportional to r. But if we are outside, it's proportional to 1 over r. Proportional to 1 over r. Okay? What is the maximum electric field? The maximum electric field is at r equal a. The electric field inside gives rho A over 2 epsilon naught. The electric field outside gives rho A squared over 2 epsilon naught A. We have A squared and A. They will cancel each other. So you see here that we have the same expression. We can say that the electric field produced by a charged cylinder is continuous at the surface. Okay, and we are done with this example. Now we will discuss the electric field due to non-conducting infinite plane with uniform charge per unit of area sigma, charge density sigma. Okay, the question here, what will be the electric field produced by non-conducting infinite plane? We have a surface charge distribution in this case. Where is the figure? Okay, good. Gauss's law said, define the Gaussian surface. You see here that Gaussian surface is a Gaussian surface is a cylindrical surface but we will define Gaussian surface based on the surface area with surface area A. Okay, with surface area A. Secondly, left-hand side said the integration of EDA, which is equal the integration of EDA cosine theta. We have, it's positively charged, so dA, it's from this side, it's outward, from this side also it's outward. So it's the angle between dA and the angle between dA and the electric field. How is it? The angle between dA and the electric field is 0. Okay. So this is the vector dA perpendicular to the Gaussian surface. dA, it's 0. But here we have also another dA for the sides. Also another dA for the sides. So we will write here for the sides plus the integration EDA cosine theta. Let's say this is theta s for the side, and this is for the ends, theta ends. Okay, what is the distance? What is the angle between dA and the vector E for the ends? Here, theta for the ends is 0. Okay, but here the electric field is in this direction. Let's say in the x direction, and the vector dA is along the y. Let's say along the y. So the angle between them is theta for the sides is 90. Cosine 90 is 0. So we will cancel this term. Okay. How many sides we have? How many ends we have? This end, and this is another end. dA. Okay. So what we're gonna do? We will multiply here by 2. Okay, because we have 2 ends. Let's say the right end and let's say the left end. And cosine theta for the end is 1. So what will be the left-hand side? The left-hand side will be 2EA. The integration of the A cosine theta is 1. So it would be E, the integration of dA. And dA is, the integration of dA is A. So this is the equation number 1. Let's move to the third step, right-hand side. Right-hand side, Q inside divided by epsilon naught. What is the charge inside this? It will be inside this sphere here. This is the charge. What will be this charge? It will be sigma multiplied by this surface area A divided by epsilon naught. This is the second term. Okay, the first term and the second term gives 2EA equal sigma A over epsilon naught. What we're gonna do, we will simplify by A, and our electric field, it will be sigma over 2 epsilon naught. So we can conclude that the electric field produced by a charged surface is sigma divided by epsilon naught. It's okay using Gauss's law. Once we are done, let's see what do we have. Yeah, this is a demonstration, the same like we did. Now, we are done with the first part. I would like to mention that all the examples that we talked about are concerning the insulators. You see here that we have an insulating sphere, an insulating sphere. Now we will talk about the properties of the conductors. What is a conductor? A conductor is a material containing free electrons that move about within it. Okay, so this is the conductor. So the conductor has free electrons, and these electrons can move through this conductor freely. What means a conductor in electrostatic equilibrium? When there is no net charge, no net motion of the charges within the conductor is said to be in electrostatic equilibrium. So we must underline here the word no net motion of charges. There is a motion. For example, if we have 5 electrons is moving to the right, but in the same time we have 5 electrons are moving to the left. So when we calculate the net motion, it would be 0. So we can say that the conductor in this condition is said to be in electrostatic equilibrium. What are the properties of the conductor in electrostatic equilibrium? The first property, the electric field is 0 everywhere inside the conductor. It's the same. It's similar to the case of the spherical shell. When we discussed the electric field inside the spherical shell, we said it's 0. So this similarly here we have the electric field just inside the conductor is 0. Why? Because any charge on an isolated conductor resides on the surface. So where the charges of the conductor are located? On the surface. The electric field is 0 inside the conductor, everywhere inside. Okay? The third property, the electric field just outside, how much? Is perpendicular at first, and it's equal sigma over epsilon naught. Not 2 epsilon naught, it's sigma over epsilon naught. The fourth property, for an irregular shaped conductor, the charges tend to accumulate at the sharpest location. And we will take some examples. This is the demonstration of these properties. I would like to skip this demonstration. Just we have to understand the properties and to know how to apply these properties. For example, for a regularly shaped conductor, the surface charge density is greatest, sigma is greatest, where at the location where the radius of curvature is the smallest. When we have small radius of curvature here, sigma in this case, let's say this is sigma 1, okay? Let's say this is sigma, let's say this is location 2, and let's say this is location 3. Sigma 1 is greater than sigma 3. Okay, here we have a little bit sharp, but here a little bit small radius of curvature, but it's larger than the first one. But in this case, it's nearly flat. So it will be sigma 2. I repeat, for irregularly shaped conductor, the surface charge density is the greatest at the location where the radius of curvature is smallest. Okay? So in the region 1, the surface charge density is the greatest. For the region 2 is the medium. For region 3 is medium. For region 2 is the smallest. Why? Because we have nearly flat surface. And we are done. We will take some other examples. Charge a conductor with a charge inside the cavity. We will take a conductor, and inside this conductor there is a cavity. Inside this cavity there is a charge. Consider a hollow conductor shown in the figure. Suppose the net charge carried by the conductor is Q, plus Q. So the charge of this plus Q is, the charge of this conductor is plus Q. Where the charge is located, according to the properties of the conductor, we said they are accumulated on, they resides on the surface. any charge on isolated conductor in electrostatic equilibrium resides on the surface. Okay, so in this case, all the charges, all the positive charges are distributed uniformly on the surface of this conductor. But suppose the net charge carried by the conductor is plus Q. In addition, there is a charge Q inside the cavity. So we will insert here a charge Q inside this cavity. So what we're gonna get, what is the charge on the outer surface now and on the inner surface? What do we said about the electric field inside the conductor in electrostatic equilibrium? The electric field inside the conductor is zero. And to get an electric field zero, Q inside must be zero. Okay? To get Q inside is zero, there is a negative charge will be induced on the inner surface. Why? To cancel this, inserted positive charge. Okay? So we have positive charge inside the cavity. It must be a negative charge to cancel this positive charge. Why? Because we said the electric field inside the conductor in electrostatic equilibrium is zero. So what will be the charge on the inner surface of the conductor? Charge on the inner surface of the conductor, inner, what will be? It's minus the charge on the cavity, the charge inside the cavity. What is the charge inside the cavity? The charge inside the cavity is plus Q. So what will be the charge on the inner surface? The charge on the inner surface, it will be Q inner equal minus Q. Okay? Why we did that? To cancel this positive charge. And why we have to cancel this positive charge inside the cavity? Because we said the electric field inside the conductor is zero. And to get an electric field inside the conductor is zero, we must have Q inside equal zero. It's okay. This is the first point. The second point, what will be the electric field just outside on the outer surface? Now you see that we have Q induced. Let's repeat the graph. This is the cavity. This is our conductor. Our conductor has a charge plus Q, and there is a positive charge Q here. What we said there is an induced charge on the inner surface of the conductor. And we said that the charge on the inner surface is what? Is minus the charge inside the cavity. This is very important. Why we did that? To get an electric field inside the conductor is zero. Okay, so what will be the charge, the charge on the inner surface? Q inner, it will be minus negative sign. The charge inside the cavity is plus Q. So what is the result? It's minus Q. This is a part of the question. Let's move to the second part of the question. He said, what is the outer surface? The charge on the outer surface. Charge on the outer surface is what? The charge on the outer surface is equal to the initial charge without charge in the cavity. What he said here, he said, suppose the net charge carried by the conductor. The net charge carried by the conductor. The net charge of the conductor. We said here that there is a charge induced on the inner surface. So we will only subtract the charge induced, Q inner. Okay, so in our case, what do we have? What is the total, the net charge of the conductor? It's Q. So let's write here Q outer. It would be Q minus Q inner. And how much is Q inner? Q inner, we said it's minus Q. So what will be? It will be Q plus Q. Okay. So خلاص, we are done. So these are the two equations of the inner surface, the charge of the inner surface and the charge of the outer surface. And we are done. Okay. So let's see here the explanation. Since the electric field inside the conductor, the net charge enclosed by the Gaussian surface shown in the figure must be zero. Okay, Q inside must be zero. This implies that the charge minus Q must have been induced on the cavity surface, on the inner cavity surface. Okay, on the inner cavity, on the inner surface of the conductor. Since the conductor itself has a charge plus Q, the amount of charge on the outer surface of the conductor must be Q plus Q, small q. And this is the explanation in details. The charge on the inner surface is minus the charge inside the cavity. And the charge on the outer surface, it's the net charge of the conductor minus Q inner. We are done. Let's take two other examples. A solid sphere plus 2Q. We have plus 2Q, solid sphere. And the conducting shell minus Q. And there is the net charge on the shell is minus Q. What will be the charge on the inner surface of the conducting shell here? What will be the charge here? Let's take another color. Q inner, what I said, Q inner, it's minus Q inside the cavity, Q cavity. What is the charge inside the cavity? It's plus Q, plus 2Q. So it will be minus, so it will be minus the charge inside the cavity, it's 2Q. So this is the Q inner. Okay, now let's talk about Q outer, on the outer surface here. On the outer surface, what do we said? On the outer surface, okay, let me take step by step. Because I don't have space to write. Good. In this case, Q inner. What is Q inner? Q inner here, it will be minus Q inside the cavity. And inside the cavity, what do we have? We have plus 2Q, so it's a minus plus 2Q. So it's a minus 2Q. Okay, so this is Q inner. Now let's take the charge on the outer surface, Q outer. What will be? It will be the net charge. How much the net charge? It's minus Q of the outer surface, of the outer shell, minus Q inner. Okay, minus Q inner, how much? How much Q inner? Minus 2Q. So what will be? It will be 2Q minus Q, so it's 2Q minus Q, so it's only plus Q. Q on the outer surface. Okay, so we are done. Let's take another example. Okay, in this case, what do we have? He's asking about Q inner and Q outer on the outer surface, on the inner surface. Q inner, let's apply just the definition, the formula. It's minus Q inside the cavity. Inside the cavity, what do we have? Plus 3Q. So it will be Q inner equal minus plus 3Q. So it will be minus 3Q. This is Q inner. Let's take now Q outer. Q outer is what? Is Q net, the net charge, which is minus 2Q, minus 2 microcoulomb, Here he said 3 microcoulomb, not Q. Okay, so Q net how much? It's minus 2 Q microcoulomb. The formula said minus Q inner. Minus Q inner. Q inner how much? Minus 3 microcoulomb. So here we have negative sign and negative sign. So let's write 3 microcoulomb minus 2 microcoulomb, which is equal 1 microcoulomb. So Q outer is 1 microcoulomb. Okay, so this is the equation that we must to apply. This is the equation that we must to apply. That's all. We are done. Let's take another example. A solid conducting sphere with a radius A has a net charge plus 2Q, a conducting spherical shell, okay, of inner radius B and outer radius A is concentric with the solid sphere and has a net charge minus Q. So you see here, we have a solid sphere with charge 2Q and spherical shell with a charge minus Q. The question, using Gauss's law, find the electric field in the region 1, 2, 3, 4. Okay, good. This is very good question. Gauss's law said what? Gauss's law said the integration of EDA equal Q inside divided by epsilon naught. Okay, but we have conductor. Now we are talking about conductor in electrostatic equilibrium. We are talking about conductor in electrostatic equilibrium. So in the region 1, what is Gauss's surface? Gauss's surface in all the regions is the same because we are talking about spherical configuration. Let's say Gaussian surface is a spherical concentric spherical surface with radius R. Next, region 1. Left-hand side. Left-hand side is what? The integration of EDA, which is equal the integration of EDA cosine theta. The vector E and the vector dA are parallel, so cosine theta is 1. So that means it's equal E 4 pi r squared, the surface area of a sphere. Next, we will talk about region 1. In region 1, what do we have? Right-hand side equal what? Right-hand side. We are in this region, inside the conductor. Conductor in electrostatic equilibrium, Q inside 1 divided by epsilon naught is what? Is 0. Why it's 0? Because the charges on the surface only. There is nothing inside the charged sphere. Okay, so it's 0. And we are talking about electrostatic conductor in electrostatic equilibrium. So that means E1 equals 0. Region 2. The right-hand side is what? Where is the region 2? Region 2. We are outside the first conductor, but inside the second. What will be Q inside? Divided by epsilon naught. It's the total charge. How much? It's 2Q divided by epsilon naught. So we will write E2 equal E 4 pi r squared equal 2Q divided by epsilon naught. So what will be? It will be 2K Q divided by r squared, by equality between the first term and the second term. Okay, let's continue. On the third region, okay, we are here now, in between. the spherical shell. Okay, so in this case, the right-hand side gives Q inside 4 divided by epsilon naught. What do we have here? We are in which region? We are inside the conductor in electrostatic equilibrium. Conductor in electrostatic equilibrium. So the electric field is 0. Okay, region 4. We are outside. Right-hand side gives Q inside 4 divided by epsilon naught. If we are outside, we are here. What do we have inside? We have 2Q and minus Q. So it's 2Q minus Q divided by epsilon naught. So it's a Q divided by epsilon naught. So equation 1 equal equation 4 gives E 4 pi r squared equal Q divided by epsilon naught. That means E equal K Q over r squared. And we are done. This is the electric field outside. Okay, we are done with the 4 regions. And thank you so much. Let's move to the class activities. A conducting spherical shell with inner radius A and outer radius B has a positive charge Q located at the center. The total charge on the shell is minus 3Q. And it's insulated from the surrounding. In the region between A and B, we are here. What is the electric field? The electric field points radially outward. The electric field radially inward. The electric field is 0 or not enough information to decide. A conductor in electrostatic equilibrium. The electric field inside is 0. Okay, directly. Property number 1. Electric field inside a conductor in electrostatic equilibrium is 0. Outside is perpendicular to the surface and equals sigma over epsilon. A solid spherical conductor has a spherical cavity in its interior. The cavity is not centered on the center of the conductor. If a positive charge is placed on the conductor, this conductor has a positive charge, but there is nothing inside the cavity. If a positive charge is placed on the conductor, the electric field in this cavity, how much? Directly, it's 0. There is nothing inside this cavity. Q inside is 0, so it's 0 also. We take this example. For which of the following charge distribution would Gauss's law not be useful for the calculation of the electric field? In uniform charged sphere of radius R, uniformly charged sphere with radius, we are done with this. Second example. Example 2. A spherical shell with radius R and has a charge uniformly distributed over the surface, it's also done. Example 3. Let's move to D. An infinitely long circular cylinder of radius R with a charge uniformly distributed over its surface, uniformly long. We talked about uniformly infinitely long circular cylinder with the charge distributed over its volume. This is example 4. But this also can be done. This can be done. See example 5. Okay. Gauss's law which we use for all the electric field, all the cases. Let's come back to the propositions. Right circular cylinder with radius R and height H. What's the difference between example 5 and C? Example 5 and C differ by the following. In example 5 is infinitely long, but here we are talking about a finite length. When we are talking about a finite length, it's difficult to calculate the electric field using Gauss's law because we have an electric field produced by the sides and an electric field produced by the ends. In this case, it would be a little bit difficult and a little bit complicated. So the correct answer will be C. Thank you so much, everyone, and see you in another lecture.